that I use the vmstat-i is because of some of the additional fields it shows you. So you'll see that it shows you this R, B, and P. R is the run queue. That is threads that are what I used to call in and ready. They're basically ready to be dispatched, but they're not getting dispatched for some reason. Now, if you look at my LCPU is 22, it's not uncommon to see twice your LCPU in the run queue, and some of that's because we have these logical, these last recently used daemons, the LAUDs, and some other processes in the system that are just around, and they may be ready to run and not necessarily getting dispatched. In this case, it's, quite often it's like in the 70s and so on, so you might want to look at why things aren't getting dispatched. You also notice that I have, on average, somewhere around the 300 threads blocked waiting on some kind of resource. That could be I/O, it could be memory. The P column typically refers to raw I/O. If you have raw I/O in the system, you may see some numbers here for I/Os that are blocked. The reason that I like this one over the default vmstat is because it gives me my real paging numbers. It gives me the actual pages in from page space and the pages out to page space. Then to the left I have pages to and from file systems, which I would expect to see. Now if you look at this free rate to scan rate, what this is telling me is how many pages did I have to scan to free this many. So I had to scan 244,000 pages to free 93,000. I typically look at that and I take a ratio and go, okay, if it's less than 4 to 1, I'm usually okay with it, but let me see what my page in, page out are. And I also would look at the free, but in order to understand what we really mean with that free column, which is this one here, you need to understand what min-free, max-free, and memory pools are set to, because there's a calculation around that. And min-free and max-free control at what point I start page stealing, at what point I stop page stealing, and at what point I am page thrashing. So those are actually important. The other thing I tend to look at is the output of an svmon, because I'm trying to figure out the breakdown of memory. Now, when you look at the svmon, it reports everything with these numbers here, which are pages. I personally don't tend to think in pages, I think in gigabytes. So I stick these into a spreadsheet, and the numbers that I'm looking at are, okay, I've got 176 gig of memory here, of which 91 gigs in use, and 13 gig is pinned. So I look at this over time for an LPAR and I go, okay, wait a minute, it went from 7 gig today to 25 gig. Somebody changed something. Did somebody pin some memory pages? Did they increase the size of the SGA? Did they pin the Oracle SGA? What did they do? Down here, it takes that pinned and it basically breaks it out for me. So here's my working storage, which is basically the actual application buffers, that kind of thing. Persistent would be typically file systems that for some reason are pinned. Client would be pinned stuff for the network. And then there's pinned large pages. It then does the same for the in-use. So up here we have our 90 gig of in-use. Now down here it breaks it down to working, persistent, and client. So it's quite useful so that you can figure out what the breakdown is of your actual memory. All right, I mentioned IO8 earlier, and I said I would come back to it, so that's what we're going to talk about now. There is a lot of confusion about high IO8. If you see high IO8, that does not necessarily mean you have an IO problem. And if you see zero IO8, it does not mean that there is not an IO problem. The thing that IO8 measures is the percentage of time that a CPU was idle and there was an IO outstanding. If there's no IO outstanding from that CPU, but there is one from another CPU, that CPU would record 0 time. So to give you an example, because it's much easier to look at a picture, if we look at this picture, this system shows 0% idle IO wait. These 3 red threads are blocked, but I have 4 threads executing. So every CPU is doing work. Nobody is waiting on IO wait as far as the CPUs are concerned, but we have 3 IOs outstanding. So this would show as 0% IO wait. Conversely, if all these yellow threads went away and I just had the 3 red threads and CPU 1 was doing nothing, I would see 75% IO wait. Because even though there's no work to run, I have 3 threads that are blocked and no other threads ready to run. So it would say, well, 75% of my CPUs are waiting on an IO, therefore you must be 75% IO wait. So IO wait only matters if there's workload waiting to run. That's all blocked on the IOs. So just be aware that it's not that you shouldn't look at IO8, but it can be misleading. So you want to monitor the system when it's well, and then see if you can actually look at the IO8 and see if it changes. Then it will give you an idea that you may have to go and look down at some other things. Okay, so this is a listing of the kernel I/O layers, and I'm just putting this in so you can see what an I/O goes through. When I look at an I/O, basically I go through the logical volume manager. I have to build an initial buffer. I then go through and I choose a JFS or a JFS2 or a network or whatever kind of buffer, and so on until I get down to getting dispatched to the H disk and then out to the actual adapter. So I/Os don't go out immediately. And that's really what this is showing you, is really how this diagram breaks down. So the first thing that happens is logical volume manager requests a pinned memory buffer. And we start to build our I/O request in the LVM layer. We then take that I/O request and we place it into either a page space buffer or a file system buffer. There's three kinds of file system buffers: JFS, client, which is NFS and Veritas, and then one that shows as external pager, which is JFS2. And you can see these if you do a vmstat -v. If it's a page buffer, then we need these things called PS buffs, and those are used to hold requests to and from page space. So the thing about PS buffs is the size of the PS buffs is determined at boot time based on the number of page spaces you have and the size of them. So if you need more PS buffs, there's only two ways to get them. One is to increase the size of a page space buffer, of a page space, and reboot. And the other way is to take and create a new page space and add it. Adding additional pages to a page space is not going to automatically increase PS buffs because they're calculated at boot time for that page space. So then, whether it's an FS buff or a PS buff, it gets queued to the actual H disk or LUN, and that queue is controlled by queue depth. Queue depth is enforced by MPIO drivers. And it's an important point because a lot of the times you'll get into discussions with your storage admin who want to give you one H disk for everything. And really, because the queue depth applies per H disk, you're probably going to want multiple H disks so that you can push more workload through. And then those get queued to the adapter, which is controlled with num command alums. And then finally, it goes out to the disk subsystem. So here's an example of the vmstat-v output, and you can see it tells you memory pools as well, which I forgot to put in here. But you can see my min perm is 3, my max perm is 90, num perm and num client are equal. Now num perm refers to all file system buffers, JFS, JFS2, NFS, Veritas, etc. Num client is a subset and only refers to NFS, Veritas, and JFS2. Typically when they're equal, that means you have no JFS in the files in the system. So when you look at the lines below, you'll see that there's 2,048 file system IOs blocked with no file system buffer. I have no idea why, but all the systems that I have that have no JFS in them seem to show a number around 2,000. I see it all the time, so if you see 2,000 there, don't worry about it. Remember also that this is since boot. However, when you look at this, we see 14.5 million pending disk IOs blocked with no PS buff, with no P buff. So, going back here, that's that very, very first one. So I'm trying to get pinned memory buffers to actually even start building my IO request, and I can't. And by the way, when these queues down the bottom get full, everything starts to back up. So sometimes, you see a problem with page space buffers or with queue depth, but the problem could be higher or lower. So we also have 1.4 million pending disk. There's 11 million page space IOs blocked. So you're doing some paging for some reason. Now you could be paging because you have a queue depth problem and everything's backing up and stuff's getting context switched. You could also have a legitimate paging problem, so you have to look into that. And you've got 39 million JFS2 buffers where it blocked the IOs because it couldn't get a buffer. So this is not a well system. So we call this a tuning opportunity because there's clearly some things that need to be done for the system. I mentioned adapter queue problems. So in Nmon Analyzer, there's the BBBF tab if you use those flags that I gave you. Or you can run vmstat. And it's going to show you, for each fiber adapter, 3 parameters that you care about. The first one is the no DMA resource count. The second is the no command alums count. And the third is the no command resource count. And basically, if you're seeing numbers in no adapter elements or no command resource count, then you need to adjust this num command elements. That is queue depth for the adapter. The no DMA resource is a direct memory area that is on that it uses for the adapter to move things around. You would make these changes in your VIO server, but if you're using NPIV, you need to make sure that your VIO server is the same size or larger than whatever you set your clients to. With NPIV, you have to set it in both the client and the VIO server. And I make this point because if you make the client bigger than the VIO server settings, your client won't boot. Just be aware of that.